under that. So this is to say, none of of the potential clients might see these secrets from the supplier, so that would suggest they cannot rely on those secrets. So later on, let's say if you change your secret, let's say from array implementation to linked list implementation, so this part, since they are secret, they won't affect the clients. So that's really the essence for information hiding. Yes?
Can you say it again? I didn't catch it.
Huh?
I didn't understand what's the non-features.
So none basically is the bottom at the hierarchy. So that means none of the, okay, so if you put any here, that means any of the clients that's actually a subclass of any can actually call the feature under this section. And since any is actually a parent class of any class, so that means any clients can use it. On the other hand, if you put a none here, because none of the classes ever in iPhone will be a subclass of none. So that means none of the classes can ever use the feature here except for the supplier itself.
But if I use the inherent none, what will happen?
You don't usually inherit from none. I don't think you can do that.
Oh.
Okay, so we actually saw this interface, Java interface last time for the map. So the key message is, all you get, although you get some type information here to say what the exceptions you might get by using the map class from Java or map interface. But all the specification here, or kind of like like a usage manual for using this class, they are really written in such a way that's informal in English. And different people using this class might have different interpretations of how it should be used. So it's not really precise and complete. So that's why we really want to introduce you to the idea of ADT first. And then it's a really formal and precise way of describing your functionality of the class. And then we'll show you how you can translate that into iPhone. Because in iPhone, you do have a contracts mechanism for you to do that. And in the later part of today, we actually show you that, remember in 1090, you actually learned about the quantifiers, like a universal quantifier, existential quantifier. I don't think this should sound too unfamiliar to you. So for those quantifier expressions, for some of them, you can actually translate them directly to iPhone, quite straightforward. So you can write very, very expressive contracts, but with cautions, of course. That will be part of the later lecture today. Okay, so that's Java, which is not really satisfactory because it's not really precise. We want precision is important if you want to get the correctness in place. Okay, so we talked about the idea of ADT. So what's really unique about ADT is really the properties that you can expect from your abstract data type. So let's see some examples. So these might be too abstract to you. So here we actually saw some properties here. So here, axioms are something that you can assume to be true, okay? Are something that you can use to prove other properties, okay? Like a mathematical axiom. Let's try to read this. So here we say we're defining a type called stack, and that's parameterized by generic parameter g. And by now, we should be able to know this g here should not clash with any known class name, right? This is to say, somehow, I don't quite care when I define the code, when I later on define the functionality of this stack class, I wouldn't care what G will be instantiated into. All I care is I'm going to realize the first in, last in, first out property for the stack. That's the most crucial property I want to realize. I can store a stack of person or a stack of account or any type. But the last in, first out is the most important property. Okay, so here, I realize this might be too mathematical, so I just want to give you some intuition. I do have another mini lecture, maybe next week, to show you more mathematical details. So here, you can see the arrow here. What does that mean? Implies? Yes. Implication. Okay. Well, that's not, well, although it's something completely different, but remember, implication is actually double arrow, right? That's implication, okay? Then? No, it's not then. Yes. Mapping, a more formal way to say would be a function. So basically, this is implication, logical implication. And by the way, if you have P, it implies Q. And if you recall your 1090 definition, that would be equivalent to not P or Q, right? So please review this if you forget about that. That's very important to know later on. And implication, and in IFO, we have a keyword called implies. Okay, that's a keyword in IFO what we use logical implication. And now, this arrow here is actually a function. Let me turn on the lights. No, it doesn't allow me to do that. Okay. So here, the arrow here, so this is called a total function. Okay, and you see an arrow here with some diagonal line, short line there. What's that? It's also a function, but what's the name? What's the
Not total.
partial function? Good. Partial function. And what's the difference between partial function and total function? Anyone? What's the difference between partial and total? No one? Okay, so you're supposed to know. Okay, so basically the idea, so remember for a particular function, you have the notion of domain and range, right? So let's say if I have a function, let's say a function, let's take from a student, actually, you know what? I think I might say your U ID. Okay? Let's say this is a function which will map from a person. So this person, okay, this is what we got first. Person into some integer or a string maybe. So maybe your YUID. Okay? So let's say this is a function, for example, I might say your U ID, and let's say some person, I can make this into a string as well. So let's say it's let's say Jonathan here. Okay, that means I'm trying to apply this function on this value here, and let's say that is simply, let's say, YU, for example, right? So that's a string. So that's one possible application of the function, right? So we call this the domain of the function, and we call this the range of the function. So you see here, YU231112 is one possible value for the range. And here, Jonathan here is one possible value for the person's name, let's say, okay? So now, if I say this is a total function, that means if I give you any person's name, you can always give me back a York UID. Is that really the case? If I give you my mom's ID, you wouldn't be able to get a York UID, would you? Because she's not registered at York University, right? So in this case, a total function wouldn't really make sense because there's some precondition on this function in some sense. Because not necessarily all the person would have a York UID, right? In this case, we should say that's a partial. That means this somehow, let's say if this is the set of person here, okay? So let's say some part of them is actually from the York U, versus the non-York U. For example, my mom is also this category here, and you can only get a value from this function here if your value here is actually from this subset, right? And they can map to their, let's say, this York UID here. So that's the range set, right? So that's the idea of partial function. So whenever if your function doesn't really apply on all the possible domain values, they should be partial. Okay, that's a brief review of your maybe 2090 or 1090 stuff. So I'll try to give you a more thorough and precise maybe tutorial maybe next week. Okay, so just want to refresh your mind a little bit so you can understand this example more properly. So now, here, let's have a look at the first function. So basically, we are trying to specify the functionality of the stack using different functions. So now, let's say for the push operation. So we are saying So now this is a function with the domain being a stack and some value. And it's going to return back to me another stack. The reason we are having stack in the beginning and the end, I mean the domain and the range, is because now we are not programming. We are trying to model the states as a function. So that's why we take the state of the stack, apply the G to push the G into it, and then we try to return a new stack. So for example, let's say if you have, so let me just give another, so for example, you can see there's another function, say, here new, so new will simply return a new stack, which is empty. So if I simply say new, yes. Is this your first class?
Yes.
Oh, okay. All right. Welcome. Okay. By the way, we got lots of videos on the web, so you can start watching it. All right. So now, because the new is actually a function that will actually return a new stack, right? And somehow this new here satisfies the domain value for the put, right? Because here you can see the first argument for the put function is actually a stack. Okay? So we can say, let's say so now we can say put. So put is a function there, right? So here we try to put in, so some empty new stack, and then we try to put, let's say 1 in there. So this is another stack. Okay? So now let's do another one, just to see. And now, given some stack, which is non-empty, that's why you see it's a partial function, because, so this is like a peak or top method in Java. So this is to say, it is not always possible for you to get a top of the stack, because when the stack is empty, they have no top, right? But that's why it's declared as a partial function. But in this case, we have an initially empty stack, but now we put some item into it, so this is new stack. And now, we can apply this new expression here as the argument value to that. So we can say item here. Okay, and now it should be equal to 1. Right? Okay, that's actually how you play with the functions. Yeah. Okay, so you can see that we also have remove. So remove is also, okay, you can see the put is actually a total function because assuming that there's no upper bound for the size of your stack, you can always try to put new elements into it. However, for the remove function, you cannot actually apply the remove on the empty stack, so that's why it's partial. And here also for the item similarly, as I said, and also given the stack, you can actually check to see if the stack is empty. So for example, so if you have a new stack and you try to apply the empty function into any stack S, then if we look at the top of the stack after we push it, it will be just the X we just pushed. It's very straightforward. And here, if we put X into some stack, and then we just remove it from there, and then we just get back to the original stack. It's also very straightforward. So you can actually look at this quite yourself. So don't really panic too much. Somehow, there's still some distance from this ADT here to the IFO class. But I just want to show you this is how you do things precisely. Okay, so here we have the precondition, exactly what I said. So that's why these are the partial functions. Okay. And how does this actually relate to the object orientation we have? Let's say in Java or iPhone. How does this relate to that? A key word to know is encapsulation. Okay? As I said before, for example, let's say for the put function here, you can see in the domain we have a stack. In the range, we also have a stack. You can think of the stack here is actually the stack before the put operation takes effect. And the stack over here is actually the stack after the put operation takes effect. So in object orientation, the idea of encapsulation is we try to organize all the attributes that are relevant to the stack into a stack class so that we can use a dot notation. So let's say, so we actually made a comparison. So in the ADT notation here, so we have put. So let's say we have stack of, let's say we simply have stack of integers. Okay. So instantiate G in the ADD. Now, let's say in iPhone or in Java, where we have the encapsulation. Okay, in this case, we actually have, so here we say S is a type stack of integer. So in this case, all the relevant information is now encapsulated into this particular instance of S, of type stack. So that's why you can say now S dot put, let's say, you can put some integer here, let's say 1. Okay? So this would be the encapsulation of all the relevant information, rather than having a stack in the front and in the end. Yes?
So you can see the example.
Okay.
Can you remove that?
Most of us can see the board.
Oh,
like
okay.
in the bottom right.
Okay, I'll try to, okay.
Bottom right you can see.
Okay, so can you see up to here?
Yeah.
Yeah, okay, just the iPhone Java part.
Yeah.
Okay, maybe I should repeat. So let me just say mission means we're trying to group the relevant ideas into a single class under some single name. For example, class or account. Okay, in this case, so rather than having stack in the domain and in the range, we will have simply declare cell stack of integer here. Okay, and then we say S dot put. Okay, so basically, in this case, this object here for stack actually encapsulates all the states for a particular stack. Let's say before this put takes place. Let's say this is stack we have. Let's say we have 2 and we have 3. Okay. After this, we actually get the same S over here, but now we actually get 2, 3, and now we get 1 at the top. Okay. In that case, it will be the same actually, but the arrangement will be different. So that means, given this stack here and this one here will return this stack, but here it's actually simply a command. Okay.
Mm-hmm.
Yeah. So we should revisit this later in the course. So don't worry too much, just to get that idea. Okay. So now. Most part of this slide would be some example for you to go over. So let me explain the basic idea, and you're supposed to do representations for that. So now basically in your class, so you want to have a class point, and you have several features there. So you have X, Y, and also you have row, and you have data. Okay? So I think most of you are most familiar with the first representation, which is just to give the coordinates, right? For example, this one can be, let's say this is 0, 0, right? But let's say I'm trying to represent this dot over here. It can be, let's say this is 4, this is 3, sorry. This is 3, let's say. So this will be 3, 4, right? So basically this stands for the origin. Okay, that's the first representation of the features here. And once you're given this, it is actually possible to convert this into the polar representation. The intuition here is, so you can see that x here is the distance from 0, 0 to here, right? And y is the height of the point. And let's say the polar representation here is to see what's really the distance from the origin to the points, and what's the angle from there. And from there, you can actually calculate what's the x and y accordingly. So either you're given x and y, which are straightforward, or you're given rho and theta. Yes?
Why is the angle a partial function exactly?
So the point, let me see. Okay, so basically you see either you're given x and y, and given x and y, you should be able to calculate theta and rho, or the other way, if you're given rho and theta, you should be able to calculate x and y. Okay, so I'm not going to spend too many details here because they have the the feature for you to calculate cosine and sine. So that's how you, given x and y, how you actually calculate the, given the rho and theta, how you calculate the x and y. Okay, so that's what you should do when you do exercise. Possible ways for you to implement the representation of the four features. Either you actually convert from x and y into rho and theta, or you convert from rho and theta into x and y. Either way. Okay, you should support both. Okay, that's ADT, and okay, that's some axiom here. That's exactly what I said. We can go over that. So ADT, and so also inheritance, we're going to talk about it next week. Okay, that's how you define the point class. So we have x and y, and we have rho and theta. And now, this is not really the contract view for this class. If you switch to the contract view, what's going to happen? The do and block will be completely hidden, because the contract view will be how the clients perceive your supplier class, which will show no implementation sequence. As far as the client is concerned, it's actually the uniform access principle, which is a very, very important property to know. The uniform access principle says that me as a client, I don't care how you actually calculate x and y and rho and theta. Maybe you actually calculate x and y from rho and theta, or maybe x and y are simply attributes. I don't care. As long as you do the job, I'll be happy. Okay, that's something for you to try. Okay, that's the uniform access principle, which is exactly what I said. So you have to know exactly what uniform access principle is. For example, in the test, I wouldn't ask you to define what a principle is. I might give you a piece of code and ask you, did it actually satisfy or obey the uniform access principle? Yes, why? No, why not? If not, then how would you fix that? Okay, that's sort of the question you can expect in the test or exam. Okay, please go over this. And so here, again, so you can actually calculate different features here. For example, you say you want to move by this distance on the x and this distance for the y, and how would you do that? For example, you might move from this point here to this point here. And to actually do that, you have to know point diagram to see how the objects are instantiated, which is exactly the behavior you saw from your Java program. So there should be no surprise here. Okay, let's say we create P. The reason that we can say so we create P and create Q. So basically P is a reference to some objects of type point, right? And Q is simply another one. Since P and Q are actually from different creation clauses or creation instructions, so they should be different. They should belong to they should be references that belong to different objects. Okay. So now we are trying to do p.move because so when you say p.move, what does that really mean? So that means trying to call this feature move on the objects that is referred to by the reference p. Okay, so we are trying to call this move here to this object here that's referred to by p. So it has nothing to do with q. Okay, and where do we find the definition here? We have to go to the class. So remember in the previous slide, we actually have the move here. So simply apply that definition there to do the updates. Okay. So now, once we have done that, we can also do just scale the points by, let's say 0.5. Okay, just another commands. Make sure you really understand the difference between commands and queries. What are the difference? What's the difference? Commands and queries, yes.
The command just performs an action, doesn't return anything, and query returns
something. And shouldn't really modify these things. Yes, very good, very good. Okay, good. So now, and also we can do some feature call here, that's just expected. Okay, now this is really crucial here. What does that mean when you say P is assigned to Q? Okay, so this means P is actually going to point to wherever Q is currently pointing to. Okay, remember the diagram before, the diagram before is simply like that, right? P is pointing to this object here, and Q is pointing to here. When you say P is assigned to Q, So he is going to, instead of pointing to this current object here, he's going to point to wherever Q is pointing to, right? That should be also familiar to you, so I don't need to spend much time. Okay, so very easy. So now we actually say a class is both a module and a type. So basically, you want to say the module, the difference between a module and a type is, module is more about what kind of interface you are supporting from the supplier scope. Like I'm going to support the X, Y, row, and data for the point class, or to move or scale. And the type is really about what are the possible runtime instances, like what kind of points do you have at the runtime. So the crucial difference between module and type is, module is really about a static definition for your ADT or for your class, the kind of interface for your services. And the type is really about at the runtime, what are the possible instantiations you might have for your classes. Okay, that's really the difference. Okay, so now this is actually one of the possible, this is actually one of the diagrams you can generate from iPhone Studio. However, you cannot simply just give this to the TA for your submission, because you are supposed to redraw this with maybe some expanded features or contracts there for your classes, okay? But for illustration, that's okay. So now we're trying to say, so this is, so whenever you actually have, so the error here is actually client-supplier relationship, okay? So let me show you what that really means. Whenever you see this architectural diagram here, that means, of course, you have a class of C, and you also have a class of A. Okay, so now we're saying that C is actually a client of A. Okay, because C somehow declares some attributes which will use the surface from class A, right? So here you have the A of type A. So this is what you will see in ISO, but if you generate a diagram from there, this is the diagram you will see. Okay? Okay, and also, you can, in ISO, you cannot assign directly to some attributes. You have to create the commands for that. So this is unlike the Java convention. Okay, that's something you have to know. Yes? Because this is actually inherited from the parent class, but somehow we have to override this feature or to redefine this definition from the parents. So we're going to talk about this next week. So all you want to know now is if you have default create as one of the possible constructors, then in the client side, you can simply say create B. That's what you can do.
It's only the default create, all right? If I just say create,
Default create.
if I say make, is that okay?
That's okay. You can include as many as you like. Okay, so you can see that basically for the point class, let me show you. So make polar here is actually one of the possible constructors for the point, because you can initialize your points from a polar representation, or you can have, okay, basically you can see you have two possible constructors for your point class. You can either make from the Cartesian representation, or you can make from the polar representation, either way. Yeah. Okay, so that's really IFO detail, so no design just yet, but it's important for you to know the details for the programming language, so let's start with exercise. Okay, so now let's default create. Exactly what I said. But you can still write this if you prefer typing more. It's really up to you. Okay, so now, so we have the default create. So here we have default create here, so you have to redefine that. So said before, you can have two possible ways to do it. To prohibit. Okay, so this is like a repeat. So if you have no constructors declared under the create, then there's no way for you to instantiate the project, the object from the client side, because it is simply empty. Okay. Okay, now this slide is very important. Okay. First of all, so basically you don't quite need a copy for your assignment or project, but you do need twin or deep twin for writing your assignment or project, okay? And also, we're going to talk about the difference between twin and deep twin. So I think in Java, maybe it's called just clone and deep clone, right? Something like that. The similar idea. Basically, you want to somehow to duplicate your objects and return to some clients. And should you actually do a very deep copy recursively, or simply just do a very shallow copy? That's really the difference between twin and deep twin. Okay, so we're going to see different ways of copying objects. The cheapest way is simply to create a reference and do the assignment with some diagram in the moments. So let me show you some diagram here. Here to help. Okay, we're going to mainly focus on these three, but this one is also straightforward, so you can also have a look at it yourself. So now the first one is, if we say G is assigned to be A, okay? So now let's say this is before. It might be better because that's why you can do the assignments, right? If you do that, you're simply, actually maybe I can apply that so you can just do cross. If I do this assignment here, that means B is going to assign, instead of B is going to point to this one, is going to point to this one, this object here. Whatever that's pointed at by A. That's very straightforward. Okay? The second one, let's say we have a slightly more complicated data structure. Let's say A refers to this object here. Okay, let's say somehow we have two fields. This can refer to another object, right? Okay, let's say this one refers to another one. Okay, so now if we say, let's say B refers to some object here. Okay, I try to go a little bit slow because it's very important for you to understand. Okay, you can see somehow A and B have the similar object structure, but you can see that both of them actually have two fields, and each one of the fields refers to different objects in the moments. Okay, this is before we do, actually C and A. Okay. Let me change this to C. Let's say this is C, and now we're trying to do C is assigned to be A dot. This is basically a shallow copy. Okay, so far so good. This is before we do the assignments. What does that mean when we do the after we do the assignments? Apparently, the meaning will be the same. Now C, instead of pointing to where it used to point to, is going to point to a new object. And the object is now denoted by A.twin. Now how does A.twin look like? That's really the key, right? So A.twin is basically to create another object here that looks exactly like A. However, we call it a shallow copy in the sense that we don't do any recursive copy. Because you can see A actually might point to other objects, and these objects might point to other objects. So it's like a recursive graph. Right? So the shallow copy doesn't do any recursive copy. It simply do a first level shallow copy. What it does is it's going to create a new object here with exactly the same structure here. However, whatever objects that are actually referred to from the first level is going to be the same. So this is going to point to the same object here, and it's going to point to the same object here. So this guy here is A dot. Any questions so far? That's A.twin. I haven't talked about the assignment just yet. I'm saying this is what A.twin will look like. Okay, so now, if we do the, yes.
One more time.
Sure, no problem. So we call the A.twin a shallow copy in the sense that we do not actually worry about anything that's beyond the first level. The first level meaning that So here, this is the first level. So this is the objects for A. And in the first level, it has, let's say it has field, let's say, I would say attribute A1, attribute A2, okay? Also, you can see the C is also attribute A1, attribute A2, okay? So now attribute A1 is actually another object reference to some other objects. Attribute A2 is a reference to another object, okay? Now a shallow copy simply just takes the object class with, also we have A1 and A2. But now A1 and A2, they are going to refer to exactly the same objects. They will actually refer to the same from the second level for A. Is it clear? Okay, we're going to see another example. Actually, this is just one first illustration, so intuitively. Okay. So now, if we do the assignment here, so this is A.twin only. But now, if we do the assignment here, now C is not going to point to whatever it used to point to. It's going to point to this A.twin here. So that's a shallow copy. We are going to see how the shallow copy and later on the deep copy are going to make a difference. Okay? Okay, so number 3, deep copy. So we have